Oh, hello. This is second module, and we are considering the issues about the calculation method. So, last lecture we was devoted to the spectral method and direct dynamic method, to the completion of the spectral method and direct dynamic method. Also, we have considered nonlinear static method, or also called the pushover method. I will remind you these two methods of calculation, and also we have considered two basic principles of earthquake resistance construction. So, and this issue I will remind you also, and then we will consider all the equations which are related to the mm, basics of earthquake resistance engineering, and also we will consider the structural scheme of earthquake resistant buildings. So, as you remember, we have considered a spectral method, and the overall minus of this method is connected with that. This method includes only one horizontal force, seismic, one horizontal seismic force. So, and that is the main minus of that method. So then we have analyzed the direct dynamic calculation method. This method is based on the record of the actual earthquake. We can analyze it based on the calculation of the recorded accelerograms, and here we have three components of the same earthquake. It is one earthquake with three main directions according to Rx, Tx, and Zx. So these three, this is the records for three vice versa orthogonal directions of the earthquake. And this method is the best one. It is the most detailed method because it describes how real earthquake impacts on our building. So, but the minus of this method is that we cannot. It is really hard. We can, but it is really hard to calculate the building according to this method. So that is why we can use it for new structural schemes, for the new buildings, or other specific buildings which we have to calculate and to analyze their behavior in details. But for the rest of the situation, it is better to use such as spectral method or nonlinear pushover method, which we will analyze later. So this method, as we discussed, is based on the calculation for the accelegrams, and that is why when we are calculating building, for example, with the consequence class CC3, when we are considering the CC3, the building with this CC. Well, what is that translated in this way? Sorry, it is CC3 with the consequence class. So in this case, we have to use the accelegrams which were recorded on the direct at our direct construction site. So, and this method is widely used for CC3 method, for unique buildings, for the building with a big width or big height or something like that. Also, for this method, we can generate or make a synthesis of the accelegrams according to the properties of local soils. As I explained you, all the accelegrams are normalized to the level of the intensity 7. So, and if we want to calculate according to this accelegram on the seismicity, for example, 6, we have to use coefficient 0.5. If we want to calculate it on the intensity 8, we have to use coefficient 2.0, and if you want to calculate it on 9 points, so in that case we have to use the coefficient 3.3. So, and also I've explained you how to choose the correct accelerogram for each case. So, the main requirement for choosing the accelerogram is to choose the accelerogram which will work in the resonance with our building, because without the resonance this accelerogram will not give the maximum impact of the earthquake on our building. So that is why we have to compare the all vibrations of the building first. For the first form, actually it works when we are considering the periods of vibration for our building. So we have to choose the closer to our building accelerogram, to choose the accelerogram with the period which is closer to the period of all vibration for our building, and that will give us the resonance during the calculation on the direct dynamic method. One more additional issue that we have to include the nonlinear behavior of the building during the earthquake, or during the calculation on the earthquake according to this method. So, and as I told you, it is really hard to calculate the overall multi-mass building with the maximum amount of rigidities, and those rigidities are of constructions. What? А, так у меня сейчас пары нет. Это я сейчас записываю видео на следующую пару, потому что сейчас тревога, и чтобы у них было видео на YouTube. Что-что? А уже отменена, но видите, я начал писать лекцию еще, когда она не была отменена. То есть это у меня следующая пара. Сейчас этой пары нету, на этой неделе нет. Это на следующей неделе у меня будет и эта пара, и следующая, а сейчас вот пока только записываю, да. Что-что? Ну то тогда, собственно, дотильно. Я тогда записываю, они ее потом просматривают с YouTube. А на прошлой паре, которая была на 8:30, было 3 человека. Мгм. Да, пожалуйста, да, все набрал. So, and if that's so, and if in this case we will use the simplified model, so this model which includes not multi-mass and not multi-stiffness building, but a single degree of freedom with one single mass, with one single rod, rigid rod, that will give us an ability to calculate such kind of the building. So, and this will give us an ability to calculate it in the simplified method, because if we will use a single mass building, it will give us an ability to calculate it on the in the fastest way compared to the calculation of the multi-mass building. So, and this simplified procedure is well done for the nonlinear static calculation method, or in other words, it can be called also pushover analysis. And this pushover analysis also helps us to define the nonlinear displacements, not displacements, but interstory drifts for three main levels for calculation. As we told, there is a weak earthquake, or from the point of view of the exploitation level of the building, it's called immediate occupancy. Second, it is design earthquake. It is called for the life safety level. And the third one, collapse prevention. It is maximum design earthquake. So this curve can be calculated for our building according to the nonlinear static calculation method. So, and how it works, as we told previously, we make a linear structural schema of the building, and make the calculation of this building based on a spectral method or spectral response method. This is two names of the same method. Then we get the displacements and behavior of the building. And according to this, we get displacements and the behavior of the building. Based on those displacement and internal forces and the elements, we choose the reinforcement. We provide the reinforcement for those elements, and that gives us an ability to calculate it is as nonlinear building. Next step for us is to calculate this nonlinear building on those forces that were defined basic on the spectrum response method. Based on this, we make the non-linear calculation of this building. But as I told you, the main difference lies in that coefficient k1 we take as 1. So we coefficient k1 in this case we use with the value 1, because when we have used it like zero point 0.3 or 0.25 for the spectral method, we have thinking there when we were calculating it on the linear behavior. We thought that nonlinear behavior will be taken into account by that reduction coefficient 0.25 or zero point 0.3. But in this case, when we are calculating it with taking into account the nonlinear behavior of the materials, in this case, we are collecting the reinforcement, the reinforcement and the behavior of the building as the nonlinear structure. So that is why we use the same coefficient k1 with the value 1. We're not reducing it down. So then we are calculating the behavior of the each story, and here are displacement displacement according to the horizontal forces for each story of the building. So each story has its own displacement during the horizontal for during the earthquake, according to the horizontal forces. So then we are condensating it to this view. We can make it using these formulas for the spectral acceleration and the spectral displacement. And in this case, we are using it as a single curve, or we can use it also as a simplified curve that is over here. So then we are and this is the spectrum of the load bearing capacity, and here is the spectrum of the impact. So this also reduced spectrum of the impact, which describes the reduction of the impact with taking on the account the nonlinear behavior of the building. So, and intersection of these two curves gives us the point of behavior of our building on the certain soils. Or also we can define the intersection of curve of behavior of the building load bearing capacity with the calculated on the accelerogram single mass, the single irretrievable mass. And during this earthquake, this earthquake called L center 50, and according to the calculation on this accelerogram, we will get the behavior point for our building over here. So then we are corresponding this curve, so with this multi-curve, and this point on this single curve gives us this curve. So this point goes to these multi-points for each story, because this curve describes the overall behavior of the building, and this family of curves describes the behavior of each floor. So then we turns back this point to this multi-curve, and this gives us the point of behavior of each story during the earthquake on these soils. And if we will make it in this view, so this gives us the uh, load bearing capacity of our building according to each type of earthquake. So weak earthquake, design earthquake, maximum design earthquake, or even the behavior of each story during the L central earthquake or other kind of earthquakes. Oh, and we have already analyzed three methods. As I told you, first basic method is widely used is a response spectrum method, and we are using and everybody uses it. And without this method, we cannot calculate the building on the nonlinear dynamic or pushover method. So, but the next way of calculation, or we will choose the nonlinear spectral or direct dynamic method. This depends on the ability of our computer to make those calculations. So next step for us is to design the structural elements based on the internal forces which we have defined on the based on the calculation method. And as you remember, the internal the load bearing capacity of the construction is defined as a sum of the load-bearing capacities for the static and for the dynamic impacts. And internal forces can be calculated as the sum of static values, which are multiplied on the coefficient gamma n, and also uh, part of the internal forces which goes from the seismic or dynamic impacts and which are divided on coefficient m. And coefficient m, as you remember, I showed you on the GAM, gives us an ability to take into account the high speed of the impact, which make impossible for plastic and non-linear property to show them in full range. So, because during this calculation, the non-linear behavior, because of the speed of the impacts, cannot show in full range. So that is why we are using this coefficient to increase the non-linear properties of material during the calculation. Also, we have coefficient gamma s, which describes the ratio between the internal forces and load-bearing capacity, and this coefficient is the reserve coefficient. It gives additional persons of load-bearing capacity to increase the guarantee that during the earthquake our building will not fall apart. And for example, for the seismic intensity for the intensity 6 point, it will give us coefficient 0.95, or for the intensity 9, it will give us 0 0.6 or 60 or 40% in additional for the load bearing capacity. And then we have started the analysis of the general principles for the designing of seismic resistant structures. And first of all, we have analyzed the simplest buildings, and as you remember, the cause why Egyptian pyramids are still standing on their places because of their configuration. So, and the main rule of earthquake-resistant design is symmetrical um, and conform forms of plan of the building and plan or height of the building. So these symmetrical solutions are the best for the from the point of view of seismic resistance. And for example, if we have a non-even distribution of rigidities and loads. In this case, we will get the lever arm between the center of masses and center of rigidities, because center of rigidity of the building is closer to the most rigid element. And in this case, where we have two non-rigid columns compared to the one rigid wall, it is clear that the center of the rigidity of the scheme will be located over here. And center of rigidity here and center of mass here give us the lever arm, which will lead to the torsional effect for our building, which is not good. So that is why it is better to make a symmetrical solutions, not even from the point of view of the form of the building, but also we have to develop the dynamically symmetrical building. Also, various strange shapes of the building, for example, L shape or T shape or L shape according to by the elevation, give us a bit additional internal forces in the inner corners of the buildings, which also can lead us for destruction, overall destruction of the building. And here are the three main solutions for such forms of the building. For example, we can split the building on the sections by anti-seismic joints. So, and in this case, instead of L-shaped building, we'll get two orthogonal buildings by only using the anti-seismic joint, and it works both for the plan and for the height of the building. Also, fillet gives us an ability to reduce the impact of that inner corner, and also we can tighten the parts of the building to make them rigid. So it will give us an ability to consider this building and to deform it during the earthquake as a single overall structure, rigid structure. Here is the intersection of the rigid intersection of the building with the non-even height, for example, 5 stories and 15 stories. And if it is impossible to split them on the section, we have to tighten them together to make this connection as rigid as it possible. Also, it is necessary to use the lightweight materials. As you remember, the internal forces, seismic forces, are defined based on the second Newton's law. So that is why when we are using heavy materials, it will give us the increase, the larger seismic forces. For example, twice mass will give us twice bigger seismic force. So that is why if we will use light materials, it will vice versa, it will reduce the seismic force. So light materials. In this case, you can see the aerated concrete with the density D400. It is a regular situation, a regular material at our construction site. And when I've analyzed the density of that, the density of real fact the density of this material, that's what I've got. Here is the mass of the elements which are located at this palette, and I've divided it on 1.8. It is the volume of this palette, so it gives us 567 kilos per cubic meter compared to 400, which was preliminary included into calculation. So only this aerated concrete will give us the 50% additional seismic force because of its own weight. So that is not good if such situation occurs. So not only from the point of view of vertical loads, but also from the horizontal impact, such as seismic impact. So next solution for reduction of the seismic forces, it is the seismic isolation solution. So it's special elements made of rubber and metal, which dissipates the seismic energy during the earthquake. And here is the example. So the building with the a base isolation system, and here is the displacement of this building, and here is the displacement of top of the same building but without base isolation system, and we can compare it, and then we will get that these elements dissipates the most of the energy, and you can see that these deformation are much less compared to these deformations. Also, we can use dampers, which also reduces the impact of the earthquake on this part of the building compared to this part. Because of this damper, it also dissipates the seismic energy because of its rigidity. Also, we can consider such elements and other like them. Also, such solution, also seismic resistance, as we considered previously, is also connected with the form of the building. Here are the two examples of the building which describes the real behavior of the good behavior of the building during the earthquake. So next question that we will discuss today is connected with the structural schemes of the earthquake-proof building. So first earthquake-proof building, as which we will consider today, is a frame building. So frame, it is connection of the vertical and horizontal load-bearing elements such as columns, beams, etc. Sometimes we can use flat slab building, so it's beamless slab. So it's horizontal elements without beams, but only the connection of the slab with the column. Which is not good for the seismic regions, but nevertheless, that is the simplest solution, which is widely used also in seismic resistance earthquake hazardous regions. So frame buildings. Next structural scheme is confined masonry building. It is a connection of masonry. Masonry in earthquake regions is not good because the limit, according to Ukrainian code, for the seismic regions with the seismicity 7, limit amount of stories is 4. So if you want to use load-bearing walls of brick, you can build only the buildings with the amount of story which not exceeds 4. 4 stories is the limit value of the amount of stories. So that is why if you want to bigger amount of floors with masonry, load-bearing masonry, in that case you have to use confined masonry. Confined masonry, it is mixed construction which includes masonry and reinforced concrete columns and beams, which are included into the special structural scheme of the building. So, and it works in the next way. Specific technology which says next. So first you have to erect the walls on one floor for one floor, and then you will get such empty places which you have to fill the reinforced concrete and to use this masonry as a continuous framework which will goes with this building for during the whole history of this building. So next structural scheme, it is a field frame. It's almost the same, but the technology is next. If confined masonry, we have to erect walls and then fill them with the concrete. Then field frame, it is the next situation where you have to erect reinforced concrete frame and only then fill it with the aerated concrete or with masonry, and that gives us an ability to consider their behavior, their joint behavior under vertical loads, but they are not working the same way from the based on the horizontal displacement, because horizontal internal forces mm, are dissipated only by reinforced concrete frame, but the masonry is not included into the special work of this scheme under the horizontal work load. So vertical loads, masonry plus reinforced concrete, horizontal impacts only by reinforced concrete. Next scheme is a complex scheme of the building. It's not really good, and this solution also I've only found good photos of such complex scheme made of wood and masonry, but same solutions can be used for the masonry buildings and with the reinforced concrete. Next scheme is the frame tie system where we have flexible connection between column and beam, and all lateral forces uh, are on ties and on diaphragms on stiffness. The next structural scheme which we will also analyze is monolithic frame buildings, monolithic masonry buildings, or also connection of masonry with reinforced concrete. But in this case, we are erecting one wall from masonry, second wall from the masonry, and we are filling with the cast in situ concrete the space between those two walls, and that gives us a really rigid and good structural scheme. But this scheme is really expensive. So, and here we can see the table with the load bearing capacity of all structural schemes which we have analyzed previously in the order of they are descending. So the highest seismicity we have for the steel frame building, because in the regions with the seismicity 7 points, there is no limit for the amount of stories. When we are talking about the monolithic cast in situ reinforced concrete walls, we had limit 24 stories for the seismic regions. Prefabricated large panel reinforced concrete walls 20 stories. Reinforced concrete frame tied buildings 16 floors. Reinforced concrete flat slab frame with diaphragms 12 stories. Confined masonry 10 stories. Complex construction 5 stories. It's masonry with reinforcement, but which not gives us frames, special frames. Also, reinforced concrete flat slab frame with without diaphragms, and walls made of bricks, nettle stone, and small piece walls. Also 4 stories. So the maximum amount of stories we can erect from steel frame buildings, and the less amount of floor we can erect from the wait a minute, how it called? From the masonry buildings. We have one more additional level. It is aerated concrete, aerated concrete walls, and the maximum amount of floors for such buildings is 3. So that is why. That was all materials which we needed to make our practical work. And from the next practice, we will start our work. So thank you for your attention. See you next week. And next week we will start our practical work. Goodbye.